High-performance liquid chromatography, or HPLC, is a highly versatile technique that separates components of a liquid mixture based on their different interactions with a stationary phase. HPLC is an adaptation of column chromatography. In column chromatography, a column is packed with microscale beads called the stationary phase. The stationary phase beads are functionalized with chemical groups that induce an interaction between the bead and the components of a mixture located in the liquid or mobile phase. As the mixture flows through the column, the components interact with the stationary phase differently. In HPLC, column chromatography is performed at a higher flow rate and therefore higher pressure than classical column chromatography. This enables the use of smaller stationary phase beads with a greater surface area to volume ratio, which greatly increases the interaction of the stationary phase and components in the mobile phase. This video will introduce the basics of the operation of HPLC by demonstrating the separation of components of various diet sodas. There are two types of HPLC used in the laboratory: analytical and preparative. In analytical HPLC, the instrument is used to identify components of small volume, and the analyzed sample is then discarded as waste. In preparative HPLC, the instrument is used to purify a mixture, and a desired amount of each component is collected in fractions. The HPLC instrumentation consists of a series of simple components. First, the mobile phase, held in solvent reservoirs, is pumped through the system by one or more pumps at a constant flow rate. The sample is injected into the mobile phase stream by the sample injector. The sample, diluted by the mobile phase, is then delivered to the HPLC column, where the components of the sample are separated. The components are then analyzed by the detector and either saved in fractions for later use or transferred to a waste bottle. The HPLC column is the key component to the system. It is composed of a metal or plastic cylinder packed with microscale beads of stationary phase, or chromatography resin. The sample mixture flows through the packed particle bed at a constant flow rate, and each component interacts with the stationary phase as it flows by. The compounds interact with the stationary phase differently, and therefore travel down the length of the column to the detector at a different rate. The time required for a component to exit the column, or elute, is called the retention time. The result is a plot of retention time versus intensity, or a chromatogram. The retention time is used to identify the component. The peak size, specifically the area under the peak, is used to quantify the amount of the compound in the initial solution. The choice of stationary phase depends on the properties of the components in the sample mixture. The most commonly used stationary phase is silica beads, as they are an inert, non-polar material that forms microscale beads and achieves sufficient packing density. The most common type of HPLC is reversed phase chromatography, which utilizes a hydrophobic stationary phase, typically silica beads with C18 chains bonded to the bead surface. The components are eluted in order of decreasing polarity. The mobile phase used in reversed phase chromatography is typically a mixture of water and an organic solvent, such as acetonitrile. Depending on the sample, the mobile phase can remain a constant ratio of water and organic solvent, known as isocratic mode. However, this can lead to broad peaks in the case of high water content, or overlapping peaks in the case of high organic content. The mobile phase ratio can also be changed linearly or stepwise during the separation to create a mobile phase gradient. A gradient elution can prevent peak broadening of the less polar components, thereby improving the separation and shortening the elution time. Now that the basics of HPLC have been outlined, the HPLC technique will be demonstrated in the laboratory. In this experiment, HPLC will be used to separate and quantify 3 common components of diet soda. First, to prepare the mobile phase, add 400 milliliters of acetonitrile to 1.5 liters of purified deionized water. Then carefully add 2.5 milliliters of glacial acetic acid. Dilute the solution to a total volume of 2 liters. The resulting solution should have a pH between 2.8 and 3.2. Adjust the pH to 4.2 by adding 40% sodium hydroxide dropwise to the stirring solution with the use of a calibrated pH meter. Filter the mobile phase through a 0.47 mm membrane filter under vacuum to degas the solution and remove solids that could plug the column. It is important to degas the solution, as bubbles could cause voids in the stationary phase or work their way to the detector cell and cause instability in measurements. Prepare 3 component solutions of caffeine, benzoate, and aspartame, which are 3 typical components of diet sodas. These component solutions are then used to prepare the standard solutions that will be utilized to determine the unknowns. Prepare 500 milliliters of the caffeine and benzoate solutions. Prepare 100 milliliters of the aspartame component solution. Store the solution in the refrigerator when not in use to avoid decomposition. Next, prepare 7 standard solutions, each with different concentrations of caffeine, benzoate, and aspartame. Pipette the proper amount of each component into a volumetric flask and dilute to the 50 milliliter mark with mobile phase. The first 3 solutions each contain 1 component to enable peak identification. The other 4 solutions contain a range of concentrations of all 3 components in order to correlate peak height to concentration. Pour each standard solution into a labeled vial in a sample rack. Store the sample rack with samples and the remaining solutions in the refrigerator. First, set up the mobile phase and waste containers. Ensure that the waste lines are fed into a waste container and are not recycling back into the mobile phase. Ensure that the inlet mobile phase line is fed into the mobile phase container. Verify that the flow rate of the mobile phase is set to 0.5 milliliters per minute. This flow rate will enable all components to elute within 5 minutes, but is slow enough to ensure resolution of individual peaks. Next, verify the minimum and maximum pressures on the solvent delivery system. These settings shut the pump off in case of a leak or clog, respectively. Press 0 on the detector's front panel to set the blank. Rinse a 100 microliter syringe with deionized water, then with several volumes of one of the 7 working standards. Then fill the syringe with that solution. Begin with the 3 single component samples in order to identify the peak of each component. Next, manually inject the solution by placing the injector handle in the load position. Slowly inject the 100 microliters of solution through the septum port. Verify that the data collection program is set to collect data for 300 seconds, which allows for enough time for all 3 peaks to elute through the detector. When ready to begin the trial, rotate the injector handle to the inject position in order to inject the sample into the mobile phase. Immediately, click Start Trial on the data collection program. When the scan is complete, repeat the process for each of the 7 standard solutions. For each of the first 3 standards, only one of the 3 peaks appears. Note the location of the peak, which is used to identify the component. Select 3 diet soda samples and allow them to sit out in open containers overnight to remove the carbonation. After overnight degassing, draw approximately 3 milliliters of each diet soda into a plastic syringe. Next, attach a filter tip to the syringe and push the soda through the filter into a glass vial in order to remove any solid particulates. Dilute 2 milliliters of each sample with 2 milliliters of the mobile phase to decrease the soda concentration by half. Draw 100 microliters of one of the soda samples into a syringe and inject it into the sample loop. Run the trial with identical parameters to the standard solutions. Repeat for each soda sample. First, correlate the peak areas of the standard samples to the known concentrations. To do so, determine the peak areas on the chromatographs for each standard sample using the triangular method. Calculate the peak height times the width at half of the height, and use this value as the peak area. Using the peak area and known concentrations, create a calibration curve for each component and determine the least squares fit for each calibration curve. Calculate the concentration of each component in the diet sodas from the peak areas. Remember that the sodas were all diluted by a factor of 2 prior to injection into the HPLC. Based on these results, calculate the milligrams of each component in a 12-ounce can of soda. Unsurprisingly, all 3 sodas tested contained roughly the same amount of the preservative benzoate. However, the Coke products contained more caffeine. The calculated values for all components correlated well to the reported values by the manufacturers. HPLC is a highly versatile instrument, which is used in a wide range of analyses. HPLC is often used to purify peptide molecules. In this example, transmembrane peptide complexes were prepared and then stabilized by oxidative cross-linking the proteins with disulfide bonds. The proteins were then dissolved in formic acid and purified using reversed phase HPLC. The sample was then eluted using a linear gradient of 2 solvents, and the purity confirmed with mass spectrometry. HPLC can also be used to identify organic compounds synthesized in the lab. In the Miller-Urey experiment, the abiotic synthesis of organic compounds on primordial Earth was studied. Primordial gases, such as methane and ammonia, were introduced to a flask containing water, simulating early oceans. Electrical discharge was then applied, imitating lightning on primordial Earth. The water was then analyzed using HPLC coupled with mass spectrometry and compared to known amino acid standards. 23 amino acids were synthesized and identified in this experiment. You've just watched Joe's introduction to HPLC. You should now understand the basics of running the instrument and analyzing the resultant data. Thanks for watching.